Hello, my name is Sevgi Gurbuz. I'm an assistant professor at the University of Alabama in Tuscaloosa. Welcome to my presentation regarding my talk entitled Exploitation of Motion Capture Data for Improved Synthetic Microdoppler Signature Generation with Adversarial Learning. This is work that was done in collaboration with Villanova University, and in particular Dr. Monis Amin, as well as his student Barış Arol, who is now a research engineer at Siemens Corporate Technology in New Jersey. The motivation and focus of our work is really how we can use microdoppler signature analysis for the purposes of automatic target recognition, and in particular for the purposes of human gait recognition. The problem of human gait recognition has a wide range of applications, including applications that involve border control and security, perimeter surveillance, as well as civilians applications involving assisted living and remote health monitoring, where we might be interested in fall detection or determination of gait abnormalities for the purposes of monitoring a person's gait-related health. This comes up when you have individuals who are of limited mobility, such as would be the case with elderly, or if someone, for example, is recovering from stroke or has other kinds of neuromuscular disorders. Deep learning has made an amazing amount of advancements over the last few years in terms of improving the accuracy of the classifications for these kinds of applications. However, there is some challenges that we have encountered in trying to apply deep learning to these applications. And one of the main challenges that we've encountered is the difficulty and impracticality in acquiring large amounts of measured data for the purposes of training deep networks. Other issues that come up are problems that involve being able to generalize to people who we've not been able to observe before, or being able to generalize to a wider range of target classes, which we might not have been able to acquire data for. Within these contexts, there's a number of ways that have been addressed in the computer vision literature, machine learning literature, for trying to deal with the training of deep neural networks. One of these approaches is unsupervised pre-training, where you basically use the symmetry of an autoencoder combined with the convolutional layers of a convolutional neural network. And what you try to do is basically use this kind of encoding decoding process to pre-train the weights of the network, and afterwards fine-tune these weights with the limited amount of real data that you have available. Convolutional autoencoders have been shown to provide very good results on microdoppler data sets. But one of the alternative methods that we can also use if we really have a small amount of data is transfer learning. And the idea here is that you would use networks which have been pre-trained on perhaps optical imagery, and instead use that as the starting point for the training of your weights. In previous work, we've done a comparison of these two approaches. That's what's being showed on the chart that we have on this slide here. And what we found is that transfer learning is really only effective if you have a truly meager amount of data. If you have any reasonable amount of measured data, then convolutional autoencoders have been shown to yield superior performance. This is perhaps not unsurprising because of the fact that convolutional autoencoders are nevertheless trained on real data only. And if you're training with data that is from your target domain, then you're really better modeling the distribution of the classes that you would expect to see in your test data. But what happens if you're in the situation where you really have no significant amount of training data and you want to apply transfer learning? Well, an alternative approach for improving the transfer learning when we have really just a meager amount of data is to, instead of training on optical imagery, which is from a completely different domain and which doesn't really relate to the physics of the microdoppler signatures that we're trying to classify, is to this time try to generate synthetic data. So really, my motivation for the talk today is to explore and compare two different methods for synthetic microdoppler signature generation. The first method is to take advantage of motion capture data and models of electromagnetic scattering to synthesize the microdoppler signatures. And the second method is to apply generative adversarial learning. Generative adversarial networks is a technique that derives from computer vision techniques that have been shown to be effective in generating a large amount of synthetic data that has a good degree of realism to actual optical imagery. Our goal in doing this kind of work is to this time be able to generate a large amount of training data for the purposes of pre-training that will this time in turn allow us to train deeper networks with a fewer amount of measured data and give us better generalization performance. So let's now step through one by one the details of the two methods that we intend to compare. Let's start by thinking about how we might model the microdoppler signature of a person. So the way that we attempted to do this actually stems from work that we started in 2015, where we worked with Kinect sensors as a low-cost device for being able to do skeleton motion tracking. And what you see here is an image of Barish, our collaborator, who actually has a Kinect skeleton superimposed on his body. And we have a finite number of point targets that are defined in the software. And what we really use the Kinect to do is to give us the time-varying ranges for each of these point targets on the skeleton. And then we superimpose the returns from each of these point targets and use the radar range equation to emulate or to model what we expect the received power to be. And so here we have a point target model where this time we have some sigma I, which is modeling the RCS of each body part. And we have parameters that also depend on losses, the transmitter power, antenna gain, wavelength, and so forth. The RCS of each body part is usually modeled according to just the geometry of various 3D objects. We used a sphere to model the RCS of the head, and we used ellipsoids to model the RCS of individual body parts. The limitations of doing simulation with this kind of a model, however, is that you're kind of restricted to the specific measurements that you still have to acquire. So as with real radar measurements, you will still need a person that will go in front and reenact the sensing environment in front of this new sensor. Instead of a radar sensor, it's a motion capture sensor, but nevertheless, you involve real participants in trying to acquire this data. And as a result, you still have challenges that come about how you would generalize to motion, given that people have a variety of different body sizes, speeds, as well as individual ways of walking. If we really wanted to generate a large database with this method that had all of this degree of variation, then you would have to bring in test subjects to the laboratory that would therefore have all of these different traits. And so in a sense, we've generated simulated data, but we haven't really reduced the burden of the measurement process any different from what we would do with a real RF sensor. The innovation that we've had here, though, is to be able to take the actual skeleton tracking data that we have from a few number of people, and instead of applying data augmentation on an image, what we've done is we've applied transformations on the underlying skeletal model itself. So consider the stick figure that we've kind of tried to animate here in 3D space. We can play around with the time axis to emulate scaling and speed. We can play around with the size of the actual body limbs that are being animated by the Kinect data to emulate different body sizes. And then we can actually interpolate the trajectories of the measurements that we've acquired and apply perturbations on each one of those trajectories to emulate differences that we might encounter due to individualized walking styles. So in this way, by basically applying these three different types of transformations, we were able to take 55 mocap measurements, which were basically acquired from 5 different people. So we have 5 different people giving 11 samples each. And we were able to this time diversify this data into a database of 32,000 synthetic microdoppler signatures. So in order to be able to see the efficacy of this kind of synthetic data generation, we also acquired 2 different types of measured data sets in this study. We acquired what we shorthand call LOS data, which is short for line of sight radar data, as well as TWR data, which is short for through the wall data. On the slide you see here below, we've shown samples from the 8 classes of different types of motion that we acquired: standing, kneeling, reaching, gesturing with your hands or arms, sitting, falling, bending, and walking. All of these data samples were required with a 25 gigahertz CW radar with a distance of several meters from the radar system, from the radar itself. And we required the data along different aspect angles. In the case of the line of sight data, we had the test subject walk at angles of 0, 30 degrees, and 45 degrees. And in the case of the through the wall data, we had additionally 60-degree data. To the type of barrier that we had in between the radar and the test subject for the acquisition of the through the wall radar data was just a kind of a mocked up kind of plywood wall that we constructed. So it wasn't actually a real wall, but it was a wall-like structure that we inserted kind of in between the test subject and the radar for the purposes of acquiring that data. And if you look at the data itself, you can see that we have other types of artifacts in the data aside from just the microdoppler that would be attributed to the target. So there are some horizontal artifacts that are due to the sensor itself, and other kinds of noise that you can see throughout the image, which is increased when you look at the through the wall radar data. It should be noticed that we did apply the eClean algorithm on these images. So the images that you're seeing here are actually the data that we've put through pre-processing, and actually we've tried to remove as much of these kinds of artifacts and noise as possible. But nevertheless, you can see that they remain in the data. And this is really where the previous kinematic method that we've described before has some disadvantages, because even though the diversified mocap might be very capable at modeling the target signature, it doesn't have any mechanism in that model for modeling these kinds of sensor artifacts and clutter. And here is where really the generative adversarial networks might be able to provide us some benefits. So let's now take a closer look at how we might generate synthetic data using generative adversarial networks. GANs are a really cool technique, which basically use a kind of game theoretical approach with a two-player game. And in this game, the generator tries to generate new images to fool the discriminator, while the discriminator tries to identify which of the generated data is fake, so that it's trying to not be fooled by the generator. It actually has an objective function that it's trying to maximize. So in this case, we're using a min-max function. And so the discriminator is trying to maximize the objective function using gradient descent, whereas the generator is trying to minimize this kind of objective function. And so you can see the actual equation for this min-max problem on the slide here. The architecture that we actually use for the generator and the discriminator are various sizes of CNNs, the details of which you can see to the left. So in addition to kind of providing as an input a noisy data to the generator, we also have class information, whereas the discriminator takes in the data from the generator and again outputs class information. So what's more kind of interesting is to see the actual data that's being generated by this kind of AC GAN architecture. And what I've shown here on this slide is samples of data, 4 instances each, for 4 different classes: walking, falling, gesturing, and bending. And you can see that there are a number of different artifacts which are inaccurate from what you would expect given the kinematics of the problem. So if you look at the first row, third column, in one of the bending signatures, for example, you can see that there's a darkened spot between the main microdoppler signature, and this is a disjoint component. And so in actual microdoppler signatures, even in the cases where we would see noise, you really wouldn't see kind of these kinds of disjoint blobs which show up. These are things which would cause error in the classification because you would never expect to see that kind of an artifact in real data. Other examples of artifacts that you wouldn't expect to see in either clutter distributions or target distributions are examples of symmetry in the data when you have a fall. So usually with falls, you have like an impulsive peak in one specific direction. You won't see kind of a symmetric impulse in 2 directions. And we can see that often in both of these falling signatures. We also have cases where the motion might be towards the radar, whereas the simulated data shows up away from the radar, and that might actually map to a different type of class. And sometimes you can see the GAN also putting in blank spaces between the periods of walking. So you have situations where you might have an emulated signature that might more closely map a different target class, such as walking away from the radar, or instead of having an impulsive fall, you might see the GAN generate something that would be more similar to a progressive fall. What I mean by a progressive fall is perhaps the case where instead of somebody falling directly from the standing position to lying down, you might see a case where the person has an additional bump in the signature, which would correspond to the person perhaps first falling to the knees and then completely falling to the ground. As well as in the case of walking, instances where the person was apparently walking, stopping, and then walking. And so all of these types of artifacts are things that can result in misclassifications when you train on them, because you're essentially misleading. You're misleading the network during the training process. And so one of the things that we've tried to do in our previous work is we've shown that there's a huge kind of performance gap which results from these kinds of inaccurate samples. And what we attempt to do is therefore try to use kinematics, or our understanding of kinematics, to sift those out. So one possibility is to use the mocap data to define boundaries of a convex hole. What we've shown in our previous results and what we've done in this paper is we've actually used the real data to define the boundaries of a convex hole, which essentially attempts us to, it's our way of attempting to describe in feature space what we consider to be the accurate or kinematically accurate samples. And so what we'll then do is take each of the data and we'll put it through a kind of sifting process where we'll take each of the synthetic data is generated by the GAN, and we'll test whether or not it falls within a certain tolerance of these boundaries that are being defined by the convex hull. And if it falls within the boundaries, then we'll say that it's close enough to kinematically accurate data, and we'll keep that as a valid synthetic sample. But if it falls outside a certain tolerance of these convex hulls for each of the classes, then we'll say, well, this data, it has too much deviated from what we would consider to be a kinematically accurate sample. And so we're going to choose not to use that data, and we'll eliminate that from the training data set. So to kind of summarize what I've shown so far is we have now two different methods for generating synthetic data. In the first case, we take 55 samples of mocap data acquired over 7 different classes using 5 different people. And we take that small amount of mocap data, we put it through our diversification technique where we apply 3 different types of transformations on the mocap data. We acquire 32,000 different samples that we then use to pre-train 50 layers of ResNet, which starts out with initially empty weights. And then we take the real line of sight data, the LOS data, to fine-tune that ResNet network, and then use that to then test the through-the-wall data set. The second kind of processing chain we can generate with synthetic data is we instead start out with our line of sight data and use that to train and drive the AC GAN, which will then generate 40,000 samples of synthetic data. But again, the problem with the GANs is that you can't be 100% sure of the kinematic accuracy, even though it does emulate the clutter distribution somewhat, and you can see evidence of the data of some of the horizontal lines that you would see due to the sensor artifacts. We're not 100% sure about the target kinematics that are being represented. So we then put it through a PCA-based sifter, which will eliminate the samples that really fall outside a certain tolerance of the distribution that we're looking at. And that will reduce the number of total training samples we have to 31,133 samples, which we then use to train ResNet and finally test on the through-the-wall radar data. So let's now compare the efficacy of these two techniques. What I'm showing you on these 2 slides is the result for the classification results for 4 different approaches towards training and classification. The first one in the top left corner is the confusion matrix for GAN, where we use the PCA-based sifting. And this is the method with which we get the best result, where we have a classification accuracy of 93.9%. The diversified mocap data gives very close results to this. It gives 91.9%. And so I would say that a roughly 2% difference in classification performance is really quite comparable. And so, but they both give very good results when you use kinematics. Let's compare this to what we would get if we used approaches that didn't really require any kind of kinematic understanding of the data, what I've kind of termed naive methods as a result. So if we use the data generated by the GAN without putting it through this kind of kinematic assessment process, sifting process, we get over 10% less performance. We get an accuracy of 82.5%. And if we were to use transfer learning from VGGNet, which was pre-trained on optical imagery, then again, we get performance, which is in the low 80%. We get 84.2%. So as you can see that even though the difference between using mocap versus GANs as a source for simulated data is relatively small, there is a huge difference between using naive methods and methods that actually exploit some kind of knowledge of the physics of the problem. That uses some kind of kinematic understanding in the way that we're generating the synthetic data. So to kind of summarize the main points of this presentation, I just want to emphasize that, deep learning has really provided amazing results. It leverages large amounts of data so that we can learn underlying representations. But when we apply this mechanism to sensing problems, we shouldn't forget that in sensing problems, we do actually know something about the representation, aside from just the data that we're measuring. The fundamentals laws of physics provide structure to the data. And we can always generate better results if we take advantage of this known structure. This is essentially a type of knowledge-aided signal processing here, which we're applying, the philosophy of which we're applying to deep learning. And what we've showed is that even in the process of generating training data, if we take advantage of the known physics and structure of the data, in the case of microdoppler data, we're taking advantage of the kinematics because we are constrained by the way the human body moves. And if you use this knowledge in the way that you're assessing the synthetic data you're generating, then you can leverage this to generate significant performance improvements in the quality of your synthetic data, and hence in the classification accuracy that you achieve afterwards. I appreciate your time in listening to my talk. I appreciate that you might have some questions regarding my talk. I have my email listed below. It's szgurbuz@ua.edu if you'd like to reach out to me to discuss anything offline. I appreciate your time. Thanks very much, and I hope you all have a great day and enjoy the rest of the conference.